Very sorry, my video turned off right in the middle last time. And I realized that as I was writing, as I was showing the little animation there, you guys couldn't see the equation. That was right here, okay? The equation I was referring to, we talked about last time, V equals F lambda. I'm sorry you couldn't see it. What I was saying was that as the wavelength in that animation seemed to go down, we know that the speed doesn't change unless the wave changes medium, okay? Unless it changes the material it's going through. It wasn't, it was going through space. So if the velocity stayed the same, the wavelength went down, that meant the frequency had to go up, and you could see that, you can go back and look, because the amount of waves per second was increasing. It works the other way too. When the source had moved past the spaceship, the wavelength was increased, there was more distance between the waves, the speed was the same, the frequency must have gone down, okay? And this is exactly what you see when we talk about the Doppler effect. The same exact thing is right here in picture form, okay? If there's relative motion between the source and the observer will encounter wavefronts either at a bigger or smaller rate, depending on if it's moving closer or farther away. The source is moving closer to C, it's moving farther away from D, so therefore C, this person is observing a shorter wavelength, wavefronts that are closer together, therefore a higher frequency, okay? The observer encounters more wavefronts per second, in other words, the frequency seems to go up, so the pitch seems higher, okay? The frequency that this is emitting didn't actually go up, but they're perceiving it as higher. Both those statements can be true, that's fine. If the source is moving away, less wavefronts are getting to D per second, frequency seems smaller, pitch ends up being lower. Okay? That in general is the Doppler effect. If you have an object emitting waves and it's moving towards an observer, the observer will notice a higher frequency for those waves. It's moving away, they will notice a smaller frequency for those waves. Okay? Known as the Doppler effect. We can use this to predict weather patterns. Okay? Equipment either on the ground or in the sky will send beams of light towards weather systems, towards clouds, and based on how that beam reflects back to the satellite or the ground equipment, we can tell whether, based on if the frequency is shifted up or shifted down from what we expect, we can tell whether that weather system is moving farther away from that object or towards that object, so we can figure out which direction it's moving in. We do the same exact thing with stars and galaxies. They emit light that we can pick up, and sometimes that light seems more blue than it should be, okay? If it seems more blue than it should be, and we'll talk about this later, but blue light has very small wavelengths, which means high frequencies. If the light seems more blue than normal, we know the object is coming towards us. We say that that object is blue shifted. If the opposite is true, if the object is moving away from us, it typically seems to have a lower frequency and a higher wavelength. We say that that's red shifted. Matter of fact, we use redshift a lot for objects that are really, really far away. We don't even state how far away they are in light years. We state how far away they are in terms of their redshift, in terms of how fast they are moving away from us. Okay? Radar guns work that police or baseball, that they use in baseball games to measure pitch speed, do the exact same thing. Okay? They use the Doppler effect to measure how fast something is moving. Okay? So that's the last couple minutes of that. Sorry that that cut off like that. So we can put wave phenomena away, and we turn to interference. Okay? Interference is probably the most important of the topics we have to talk about in terms of wave phenomena. Okay? Interference is not a particularly complicated thing, at least at your level. Let me start again by doing the contrast between waves and particles. You take two particles, okay, right here in my hand. I have a Penn 3 tennis ball and a Dunlop 1 tennis ball. And if I throw them towards each other, they bounce off. They bounce off. They hit each other and they move backwards, okay? And I know that because the Penn 3 is still in my right hand. Looks like they're in my left hand to you guys. And the Dunlop 1 is still in my left hand, okay? Nothing weird happens. They just bounce off each other. Waves do not do that, okay? Waves do not simply bounce off one another. Okay? When waves are on a collision course, what happens is they actually pass through one another. And this is another time where it would be great if this was live and I could have my Slinky out. Because when you see this happen with the Slinky right here, then it's very obvious that they're doing this, okay? But what typically happens is you have two waves, well, these are pulses, but you get the general idea, that are moving like this, okay? And then after a little while, after they have passed through one another, you eventually end up with this, okay? Those waves just pass through one another. Continue, neither of them have changed. I know that it doesn't look exactly the same, but take my word for it, neither of them has changed at all. Okay, they just simply pass through one another. So not only do they do this though, but when they are overlapped in the middle, then you get some weird stuff happening. Okay, and this weird stuff is governed by a rule called the principle of superposition. Okay. What this means, the principle of superposition, is that when they are combined, okay, the displacement of the combined wave from equilibrium is equal to the sum of the displacements of each wave. Okay? I'll talk about what that means in a second. But another name for this principle of superposition, when waves are doing this, when they're combining and overlapping, this is called interference. Waves interfering. Now, when we do examples here, you're going to divide this up into three areas. You're going to write kind of small, or you're going to draw kind of small, because I have a bunch of pictures that are about to go here. But first, let's do two examples on a little application that I have. Okay, that's enough Doppler shift. Okay, I believe we have done this before. Let's turn the damping down. Pulse. Let's do that. Okay, high amplitude, low pulse width, and we'll do slow motion for right now. Okay, so we talked about this when we talked about reflections from a barrier. So we've got this one. It's going to reflect right side up because that's a loose barrier. But we have two triangle pulses coming towards one another. They are going to pass right through one another and then continue on their merry way. However, what do you think is going to happen when they get to the middle, when they overlap? If you're thinking that they should become much bigger than they are normally, you would be right, okay? These two waves combine to be, let me restart this. So, there's the height of this wave, there's the height of this wave. They combine to be about twice as tall as they would be otherwise. Oh, I didn't quite get to twice as tall. Okay, must have timed it just perfectly. But you saw it got up to right about here. Okay, that is what happens when you have two waves with the same orientation going. And then look, they come back right to their same heights when they are done interfering. Now, what's going to happen here is this wave is going to invert. That wave is not. So now let's try and see what happens. When that inverts, okay. Now we have two waves coming at each other. They do not have the same amount of displacement. One is displaced up here, the other one down here. What do you think is going to happen? You get some weird shapes, but look what happens right in the middle. They completely cancel each other out. And then, you know that they have just moved past each other because look, they didn't bounce off one another, okay? The one that had this sort of displacement, the lower displacement, didn't bounce this way. The one with the higher displacement didn't go that way. They have moved right through one another. Okay, they've moved exactly through one another. And they're continuing to go. I've got one more demonstration of this. Let's do, okay, pulse, and then let's do slow motion. We're going to decrease the pulse height now, about 1/2 of what it was. All right, so when these two meet, as we saw before, I'm going to assume, let's see, here's the height of one, here's the height of the next. I'm going to predict this one, since the rule is that the overall height or the overall displacement is equal to the sum of each individual displacement. In other words, you can kind of think about this as like adding heights together. This one's this tall, this one's this tall. If I add those two heights together, I should get a combined wave that gets up to about here. Let's see if that's the case. Just about. And on the way back, one of them will be lower, or so one has a negative displacement, the other one has a positive displacement. You could think of this displacement as being negative. So I'd say, okay, so let's see, I take this much and I subtract it from this. I'm going to say this one will be about here, the overall displacement. And we see when they're completely combined, that is just about the case. And then they move past one another. So we're going to draw some pictures of this. Okay. Our first example will be two square pulses moving towards one another. This is not the square pulse, it's just me dividing up my page. First example will be two square pulses moving towards one another. This one is 7 centimeters, this one is 5 centimeters. They're moving towards one another. When they are overlapped, we want to know the height. Then afterwards, we know that they should be moving away from each other, but they should still have the same heights that they had. Now, in the middle, when they're overlapped, how tall are they? Well, this one is originally 5 centimeters, this one is 7 centimeters. In the middle, that means we should have, make that a little bigger, something about 12 centimeters tall. Okay? That's how interference works. You simply add up the displacements. That's it. We could do another example where we have, wave pulses that look a little bit more like what you guys are used to. Let's say this one is 4 centimeters tall. This one is also 4 centimeters tall. What do you think happens in the middle? Should be pretty obvious from that example, but they exactly cancel each other out. And then at the end, everything goes back to normal. They have moved past one another, 4 centimeters and 4 centimeters. Okay? Our last example is going to be probably the toughest that you'll see in this class. What if you have something weird like this? Where you have, let's say, a 10 centimeter triangular wave and you have a 10 centimeter square wave. What happens when they overlap? Here's a general way. We know that afterwards they'll just be like this. Here's a quick way to figure that out. Let me grab some other markers. Okay, here's a real quick way to figure that out. If we draw it like this, okay, here's where the square would be, the square part of the wave. Go a little higher. And here's where the triangle would be. So I said earlier that the way to figure out how high the wave would be to just add the displacements. You can do that not only if you have two waves that look similar, but you can also do that if you have two shapes that look dissimilar, if you just do it at every single point. Okay? The amplitude, or the height of the green square wave here, is 10 centimeters. For the triangle, the pink triangle here, the height is 0 at this leftmost edge. So that means that at the combined point, we must have, the wave must be 10 centimeters tall. Now this is 10 centimeters all the way across, right? But this height changes, this displacement changes. It goes from 0 down to 10, and then back up to 0. So if you move over a little bit, this one's now at -1, and this is at 10. Well, what's 1, or -1 plus 10 would be 9. You add them together, that must go down a little bit. And this can continue all the way down. Okay, I didn't do as many points as I should have, but the ultimate pattern ends up looking like this. Okay? In other words, for this one, it kind of looks like the square pulse, but that triangle is like taking a bite out of it. All right? All we've done is we've superposed those two waves together. That's all we've done. Now, Like I said, this is one of the trickier ones that you could see. This is an actual AP question, okay? This is an actual question from the AP exam. And what, if your class was, this was for my first year teaching. If your class was lucky enough to have done this example, all you had to do was figure out where these overlapped. If I remember correctly, it took 5 seconds for them to overlap, so let's move this over. 1, 2, 3, 4, 5. Okay, that's there. So the first pulse looked like this when it was moved over. The second pulse, 1, 2, 3, 4, 5. Okay, so that one goes down like this. All you had to do was to kind of look point by point, okay? They're both at 0 at these 2 points, but at this kind of